we're going to look at an example of type 1, type 2 error. The scenario here is the average IQ score for adults is 100 and the standard deviation is 15. So assume the standard deviation for IQ scores among SA teachers is also 15. We want to test the hypothesis that SAA teachers have higher than average IQ scores. So we'll set up, in an example like this, we'll set up a null and alternative hypothesis. And our null hypothesis is always the neutral hypothesis. We're going to say, starting out, let's assume that the mean IQ score of SAA teachers, that's what mu is representing here, the mean IQ score of SAA teachers is 100. So HO is always the neutral hypothesis. Usually going to be an equal sign. Okay. HA says we're trying to get evidence that mu is actually greater than 100. We're trying to get evidence that the SAA teacher's IQ score is greater than 100. So first, let's look at this chart, and I like to relate this chart to our judicial system. We are always going to assume someone is innocent until we can get enough evidence that they're actually guilty. Okay, so let's see. We have a chart here. HO is true. HO is false. That's in reality, which is HO true or HO false. And here's what decision we make. Either we reject HO or fail to reject HO. And that's what we can do. Okay, so this cell right here represents, so HO represents someone's guilty. That's our null hypothesis until we get evidence that they're guilty. So HA will be they're guilty. Okay, so this is saying someone's actually innocent. If we reject that they're innocent, which means we think they're guilty, that's what type 1 error is. Okay, so again, HO is true and we reject it. That's type 1 error. So in the judicial system, somebody who is innocent but is convicted as guilty. Okay, so notice that this is the correct decision. If they're truly innocent and we fail to reject HO, in other words, if we reject HO, we're saying that they're guilty. We don't reject that, so we're basically thinking that they're innocent. So we got the right decision. In this case, HO is false would be like if the person is guilty. If we reject HO, we're saying that we think they're guilty, that we were right. That's a correct rejection. Okay. And lastly, type 2 error is if they're guilty, but we fail to reject HO, which means we think they're innocent. That's a type 2 error. So, and the reason I kind of related that back to the judicial system is you can kind of remember type 1 error is thinking someone's innocent when they're really, or thinking someone is guilty when they're really innocent. And type 2 error is concluding that someone's innocent when they're actually guilty. So when we start out a problem, let's go down here. We know that we're assuming that the mean of this distribution is 100. That it's centered around 100. And we know that the standard deviation is 15 because it says the standard deviation of IQ scores of SAA teachers is 15. We're making that assumption. Okay, eventually we won't have to make assumptions, but we're trying to understand the theory behind it, we do. So there's a certain point here where if we're going to basically take a random sample of SAA teachers and we're going to collect the sample mean. There's a point here where it's going to be high enough to where we're going to reject the fact that the mean is 100 and say that we think that it's actually greater than 100. Okay, and this value comes from whatever we set alpha to be. Alpha, a lot of times, we'll set to be 0.05. So I'll do that as 0.05. That's not that all the time, but this is the most common example. Okay. Now, we understand what's happening here. 5% of the time, even if the true mean is 100, we're going to reject, because that's what this tail is. This is the true mean, or the true curve. We're assuming that it's 100. So even if the true mean really was 100, 5% of the time, we're going to get a value out here, and we're going to reject, because it's far enough from the mean that we're going to reject that the mean is actually, or we're going to favor that the mean is actually greater than 100. Okay, so if you understand what we said, that HO is true, but we are rejecting 5% of the time. So what that is, alpha is the probability that we commit type 1 error. HO is true, so even if HO is true, and we reject 5% of the time. So that's what alpha is. Now, the problem, you might just say, well, why don't you make alpha smaller? Alpha smaller means you're going to make type 1 error less. Well, the problem with that is, if we go back to this, if we reject more often, then we also if we fail to reject more often, if we have to have more evidence to reject, we're going to fail to reject more often. So yeah, type 1 error will go down, but type 2 error goes up. So there's a balance. 0.05 is actually usually a pretty good balance from type 1, type 2 error. So again, type 1 error goes down, type 2 error goes up, and vice versa. So let me go back to this one more time. Now, this correct decision right here, correct rejection, is actually what we call power. It's got a special name. That means if HO is false, what's the likelihood that we actually reject it? Okay, and that's what we call power. If HO is false, what's the probability we actually reject it? So let's look at an example here. It says, suppose we take a random sample of 6 teachers and get a mean of 110. So in other words, this mean is 100. What if we got 110? And we know that the standard deviation. So what we're actually looking at here is the sampling distribution of sample means of size 6. If the true mean really is 100, every time you take a sample of size 6, you're going to get a certain sample mean, but it's the most probable value is going to be 100. But how much is distributed, the standard deviation, we know is 15 divided by the square root of 6. Okay? So what we're trying to do, and I'm not going to go through the computation here because that's not what we're focusing on. But what we would try to do is find out 15 divided by 6, you get your standard deviation. You would get your z-score here. And you would try to find this probability. What's the likelihood, if the true mean really was 100, what's the likelihood that you got something of a sample mean of 110 or more? So if the true mean of SAA IQ or SAA teachers' IQ scores, if it really is 100, how likely is it that you sampled 6 people and got a mean of 110? And that's what you'll be finding with this probability. Once you find your standard deviation, you can find your z-score and find that. So I want to go back and look a little bit at, and by the way, if that probability is small, below our alpha, we set alpha to be 0.05. So if it's small, below alpha, you're saying that there's less than a 5% chance that happens. We would reject HO, and that means we're getting evidence that the mean is actually greater than 100. So now let's look at this. So this is our setup. What if the mean really, we're saying the mean sub-zero is 100, it's the true mean. Or this is our hypothesized mean. We're assuming that the true mean is 100 for our null hypothesis. Okay, our standard deviation is 15. Our alpha, which is the probability of type 1 error, which is what you see right here in blue, is 0.05. That's what we set that. We can change that. Our n is 6. Okay, so what we're saying here is there's a 5% chance that even if the true mean is 100, that you get a unlucky sample, I'll call it, an unlucky sample out here, and you'll reject. And you can see that somewhere between 100 and 115. Not exactly sure what that is, but it's not important. Okay, so now what I want us to do is take a look at this. This pink curve is, what if we knew, or I guess it's not really what you know, but what if this was the true population? The blue curve is what we're testing, and the pink curve is the true value, the true mean. Notice that the true mean here is 117.7. Okay, well, if that's the true mean, notice that we will fail to reject. This is what we're testing, that the mean is 100. We'll fail to reject this red piece right here. Okay, we're failing to reject because it's not outside of our rejection region. This is our rejection region. We reject this stuff. Well, we don't reject this. We fail to reject. Well, if the mean really is that, so think about what's happening is the mean is, or our HO is false. The true mean is really not 100. HO is false, but we're failing to reject. So what's represented right here is type 2 error. And the name for type 2 error that we use is beta. So alpha is the probability of type 1 error. Beta is the probability of type 2 error. Okay. So notice that beta changes depending on how far the true value is from the hypothesized value. Notice if there's not a big difference in between the true mean and the hypothesized mean, we got a bigger chance of making that mistake. Notice that this red overlap's pretty big here. There's a 92% chance that we make an error there, or type 2 error. If they're further away, notice here is basically no chance. But if they're here, the further they're away, the smaller beta is, the smaller the probability of type 2 error. Now notice that power and beta are complements. That means 1 minus beta is power. Because what it says is if HO is not true, beta is the probability that we fail to reject, make a mistake. Power is the probability that we reject, get it right. Okay? So, a couple of things we can do I want to talk about here. If I increase alpha, let me increase it pretty large here to 0.2. Notice that this is my rejection region now. I increased alpha, which means that I'm going to reject more often. This stuff, all of this stuff I'm rejecting, okay? Which in this case is good because our true mean is, our HO is not true. So notice that when alpha goes up, beta went down. We mentioned that earlier. As alpha goes up, beta goes down. And as beta goes down, power goes up. Okay? So we're a lot of time interested in how to increase power. Because power means if HO is false, the probability that we reject it. So we're interested in increasing power. One way to do that is to increase alpha. However, as we said earlier, the problem with increasing alpha is that by definition, alpha is the probability of type 1 error. Okay, so there's a balance there. The other way that you can increase power is to increase the sample size, and we'll see why here. If, as opposed to selecting 6 people, had I selected 15 people, what do you notice is that the sampling distributions have a smaller standard deviation. So the fact that they have smaller standard deviations means there's less overlap here, which makes beta less. Notice that beta is 0 here. Okay, the larger sample size you have, the less overlap. So 3 ways to increase power. One way is to have your HO or your hypothesized mean further away from the true mean. However, there we have no control over what the true mean is and what we're testing, so we can't control that. But that is one way. The second way to increase power would be to increase alpha. We said that does increase power, but it also increases the probability of type 1 error, which we have to be careful about. So the best way to increase power would be to increase your sample size, because that makes your standard deviation smaller, which will give you less overlap.